this will be our session 11, and we will have two more sessions. I mean, the final session will be an extra session. So before that extra session, we will have a session which is, I mean, session 12. Total we have 12 sessions. So this will be session 1 last before. So yeah, let's start. So previously we have discussed different types of phase transformations. When we arrive to phase transformation, we have seen, we have broadly categorized two types of phase transformations. One is the diffusional phase transformation, and another is the diffusionless phase transformation. Right. So yeah, so there are two types of phase transformation. One is diffusional and diffusionless phase transformation. And in diffusion phase transformation, we discussed the phase transform via the movement of atoms. Right, there is a need for diffusion of atoms to form a different phase. For example, we have seen in steel, the famous example, which is a tetrahedral composition, where when gamma at 0.8% carbon, when it is cooled from homogeneous, like equilibrium cooled, above 1000 degrees centigrade to room temperature, you will find a perlite, right, which is the columnar structure of alpha, which is alpha Fe ferrite or alpha ferrite, plus Fe3C, which is cementite, right? We find the ferrite and cementite of the laminar structures. So how do they look like? They look like this, right? So this is my perlite, then this will be my cementite. Right, these are the different structures we have seen. Right, we have perlite of alpha and Fe3C. So if I have a microstructure, let's say these are my grains of gamma grains. So when I cooled it to room temperature from like 1000 degrees centigrade to room temperature, right, from 1000 degrees centigrade to room temperature, so we form let's say the grains will remain same, right, and we even have discussed where the nucleation preferred, right, inside the grain, which is again known as homogeneous phase transformation. Now if something grows on something, like for example on these grain boundaries, so one example is something might grow on these grain boundaries, right, or something might go on this mold wall, right. So when something is nucleating on the, what do we call, the mold or a different surface, right, in homogeneous nucleation we have seen that a new grain will form. In homogeneous nucleation we have seen that a new grain will form inside a system, right, but in heterogeneous nucleation we can say that new grain will form on a separate entity. Now again, we have seen that the critical radius for homogeneous nucleation and for heterogeneous nucleation will remain same, but the delta G star will decrease. Now again, the delta G star, why it will decrease for homogeneous and heterogeneous nucleation? Because in homogeneous nucleation, if something forms, if some phase of different type of phase forms, then it needs to create a surface area, its own surface area, right? So the system needs to provide energy to form a new surface. Now that goes for homogeneous nucleation, because in homogeneous nucleation, from a phase we are getting another phase, right? So inside the phase we are getting another phase. So there is a creation of a new surface area inside a volume, right? Before, for example, let's say in homogeneous nucleation we have seen that if this is my container liquid pool, then something, for example, a grain starts to nucleate at the center. Just a hypothetical case. So it happens at the center. You have a equiaxed homogeneous nucleated grains. So at the center it will start to grow. That's how we call them as a equiaxed grains. Now again, for it to form, it needs to form this new surface area. The system needs to provide the energy for the creation of this new surface area, right? Before that there was nothing, it's total volume, there was no surface there. But now there is a creation of a new surface area. Now system needs to provide to create that surface area, right? So in homogeneous nucleation, that's why it is not actually seen everywhere. And the reason is because the system needs to provide the energy for it. Now what about the heterogeneous nucleation? For heterogeneous nucleation you can see that it can form on this surface, right? This is my gamma brain, this is also my gamma brain grain, this is gamma 1 and this is gamma 2, and it is a new grain is formed on the grain boundary, right? It is forming on a boundary. So that is what I'm saying. A new grain is formed on the interface between gamma 1 and gamma 2, right? So there is a surface, there is already a surface here, right? So that is a grain boundary. So at grain we know what is the difference between gamma two grains is nothing but the of the same phase is nothing but the planar orientation, right? How the atomic planes are oriented in specific direction. For example, here gamma 1 we have 111 planes may be facing this direction. In gamma 2 you might have a slightly a different direction. So again we have discussed the low angle, high angle. I mean depending upon the orientation we have tilt axis and twist axis, right? So there are low angle grain boundaries, high angle grain boundaries, there are special angle grain boundaries, we call them as the twin boundaries. So all these things we have discussed, you can go and check them in those lectures, right? So yeah, so what is happening in heterogeneous nucleation? Now in heterogeneous nucleation there is already a surface, there's already a grain boundary. Now again the grain boundary doesn't have any symmetry doesn't follow any symmetry. Why? Because the symmetry is being changed from one point to another point, from grain gamma 1 to gamma 2. So there is no specified symmetry at the grain boundary, which is nothing but totally random arrangement of atoms. If you are talking about the coherent surface, right? So sorry, not coherent surface. If you are talking about incoherent surface, incoherent or somewhat semi-coherent surfaces. So that's why the energy is higher at there. Now to minimize that energy, the grain boundary energy, a new surface will form, a new phase will form there. So what we are trying to do here is we are trying to minimize. So for example, if I take the coherent surface, now coherent surface has a certain amount of strain. There is no perfect match, right? If there is no perfect match or there is a slight change in lattice parameter because of this change in crystallographic direction, then there needs to be accommodation of the sites of grain 1 and grain 2. Now to do that we need to strain the atoms of any of the atoms of grain 1 or grain 2. Because of that there is a straining, and to minimize this strain, so straining means we are increasing the total energy of the system. Now to minimize this strain, the system tries to grow a new phase here, that is what we call as the phenomenon is called as heterogeneous nucleation, right? Now coming back to this, so we have seen that there is a alpha Fe and there is a cementite. So they will grow parallelly like this. So one is alpha and another is Fe3C. So this is how they grow, on any grain boundary. Now this is about the diffusional transformation. Now how do they grow? So let's say this is my alpha and this is my Fe3C, right? So this is my alpha, this is my cementite. Right, so this is the alpha and this is my cementite. Now the alpha tries to spit out the solute, right? So it spits out the solute at here, right? So this carbon atom will try to diffuse from here to here, and the same goes for Fe3C formation here also, because the carbon can move in any direction, right? So carbon will try to diffuse from here to here, because Fe3C is very rich in carbon when compared to alpha ferrite. So this carbon will try to diffuse from above to sideways, right? And some amount of carbon is also rejected in this direction, so carbon will also try to diffuse into this direction, right? So, and because there is a chemical potential gradient or there is a concentration gradient, so Fe3C will consume more amount of carbon, right? So carbon is less here, now the carbon is more here, so carbon will try to diffuse from here to here, which is dou C upon dou x, and you multiply it with our diffusivity of carbon, then you will have a molar flux of carbon diffusing from above the surface of alpha to Fe3C, right? So that is about the diffusion. Now moving on to this is about the diffusion, right? So we need a diffusion for the alpha to form or Fe3C to grow, right? So this is one example of diffusional transformation, and there are many examples. I have said there is also this eutectic phase transformation, where liquid will transform into alpha plus Fe3C, and there is also the diffusion for carbon atoms at the surface, at the solidification, right? So we even have a constitutional solidification, right? Depending upon it also depends upon how the concentration will change the temperature of the system, the equilibrium temperature of the system, right? So those are the different types of phase transformations we have discussed, and also one among the diffusional phase transformation, which is the final one that we are going to discuss here, is the spinodal decomposition. Now I have given a few bits and pieces about spinodal decomposition in previous class, but again I will again go through it. So for example, here consider a phase or consider a system, so binary system. So you have pure A here, and you have this one, you have pure B here, right? So you have pure A and you have pure B. So we are only considered for binary system. It's not complicated with ternary and quaternary system. So yeah. No, and also we are considering we have a miscibility gap here. So here it is completely soluble, right? This whole region A and B are completely soluble, but below this gap we have immiscibility gap. That means we have two compositions here and here at room temperature, right? And you can set 0 degrees centigrade. We can set here at room temperature. Let's say this is my room temperature. And also once the diffusion stops, there will be no further change in composition. We will end up with whatever the composition we attain at room temperature, we will attain the same the composition microstructure even at 0 degrees centigrade, because we are not allowing any diffusion of atoms. So it will be same whether you go from room temperature to minus 20 degree or minus 40 degrees centigrade. and below minus 270 degrees centigrade, that is whole another matter, because that will be, we will be reaching another type of state, so let's not talk about that. So up to 270 minus 270 degrees centigrade, whatever you see up to room temperature, you will see the same if you are talking about high melting point metals, right? For high melting point means their metallic bond is quite strong, right? So their diffusion is very sluggish when compared to the water or ice or any other thing. Now, yeah, this is our room temperature, and we have pure A and pure B. Now, if an, for example, if I take of an alloy with composition X naught, say if I take an alloy composition of X naught, and we are homogenizing at temperature T1. And again, why do we do homogenize? We homogenize because to attain the chemical homogeneity. So at T1, which corresponds at X naught, and T1, which corresponds to the point, this point, right? So it corresponds to this point, and here it is completely miscible, right? So we see a part of we see like isomorphous diagram, but it is totally miscible. I mean, whatever the proportions you mix, A or B, they will completely mix, right? So that is what we see here. That's why we call it as a completely miscible solid solution. So A and B both are mixed, right? Now, moving on to, you know what I am trying to do is, what if I try to cool down, right? So if I know, so on taking with, so if I take alloy of composition X naught, and if I homogenize at high temperature T1, and then I quenched it to lower temperature T2, right? So I did the oil bath, not like water quenching, which will turn out to room temperature. So I maintain my oil bath at certain temperature like T2, and then I quench my sample, which is at T1 degree centigrade, to T2. Now, once I do that, the composition will initially be the same everywhere inside the sample, right? At the time of quenching, the composition is same, because we are why do we quenching is nothing but, while quenching we retain whatever the composition, whatever the phase structure is there at T1, we retain it at T2, right? Now, however, here you can see at T2, if I draw a free energy versus composition diagram, so it is at T2. Right, so I am drawing the free energy versus composition diagram at a specific temperature. Now we have seen the free energy versus composition diagram at for different temperatures, for different types of phase diagram. We did draw the free energy versus composition for the isomorphous phase diagram, for eutectic phase diagram, for eutectoid phase diagrams, and quadratic phase diagrams, and different, even for isomorphous, even for this binodal decomposition or spinodal decomposition diagrams, right? So I will clear it what's the difference between binodal and spinodal in a few minutes. For now, let's see how this thing is happening. So this whole part is my, so this from here to here, these black lines, so these black lines are nothing but the immiscibility gaps. So I'm going to discuss why these things are happening. So I draw the free energy versus composition diagram for at temperature T2 for this phase diagram. Now you can see we have one point here and another point here. So, and also the maxima here, and we have one inflection point two inflection points, sorry. So these are two inflection points. Now why I am saying inflection points, because the double derivative of the g is 0 there. That means the g, the slope, the dg by dx, yeah. So here what exactly happening is the dg upon dx will change its sign, right? So the dg upon dx will continuously change from positive to negative. So that's why the double derivative will either show negative or will show positive. So below it will show positive, and above it will show negative. So that's why the dg by the first derivative of the free energy will change its sign, or it will change, the slope will continuously change its sign from here, let's say from here to here. So that's why at first you have a positive, so the change will be positive, and then once there will be a position where the change will be 0, and other again a position will be there where the dou g upon dou x will be the dou square g upon dou x square will be negative, right? So the slope will change here, it will have the change will be positive, and here the double derivative will be 0, and here the double derivative or the slope change will be negative. So that is what it means. So I have g as a function of I have g as a function of composition. Now so I have a free energy as a function of a composition. Now first, if I do the differentiation, or if I do the first derivative, so if I do the first derivative, I will obtain the slope, right? So that's what we do. I will obtain the slope. Now if I do the double differentiation, it will tell us how the slope is going to change with respect to x, or at a certain point of x. So that is what we mean. So below this inflection point, I have that, yeah, below this inflection point I have one type of slope change, which is positive. That means the slope is continuously increasing. Here I have, at one point I have 0, and then the slope will continuously change to be negative. Right, so that's what we can see. Here the slope is 0. Right, so tan 0, 0. Again, the slope is 0 here. So again the slope is 0 here. Now the slope will try to change, right? It will try to increase. So it will try to increase. Again it will start decreasing, because at one moment of time the slope is 0 at that point. Right, so we have either two cases. One, the slope is 0 here, again it is 0 here. So we have two cases. One, the slope will either have to remain same, or the slope has to decrease and increase, or it should increase and then decrease to 0. Right, so when we are starting with 0, that means the slope must increase, right? That's what we are seeing here. Or if it starts to decrease, so let's say if from here, from this point, if the slope starts to decrease, then it will look like this, which is not the case, right? So if the slope wants to change these points, then it should go like this. So that is what's happening. The slope, at first it was 0, and then it starts to increase, and it starts to decrease, and again it will become 0. Now that is one case. Now what was the first case? The first case was the slope doesn't change. If the slope doesn't change, then it will more or less looks like this. So again, which is not the case here. Hence Bernoulli composition. right? So our case is the slope changes in this manner. So that's how we see our the decomposition. Now let's move on to the next slide. So before explaining this, let me add one more slide. Let me add one more slide. Now the next question is how do we get the inflection point, right? So that there must be some mathematical way. So that's, and we have done this already, so don't worry, I will do that again. So while writing for delta H mix for non-ideal cases, for ideal cases our delta H mix is 0, right? And for non-ideal solutions or for regular solutions, the delta H mix is non-zero, and it depends upon omega times XA upon XA times XB, right? So these are the terms, and it also, and this term, this omega term, depends upon the bond energy. And this omega term, it depends upon the bond energy. Now how does it depend? Now we know the bond energy difference, right? So before or after the reaction, which is before it was AA and BB, and after reaction it was AB. For example, it forms an AB. So now if AB forms, then delta H mix will be 0. So sorry, not 0, it will be negative, right? So if our final product is AB, if it is more negative, then negative AB minus bond energy of AB minus of half times bond energy of AA plus bond energy of BB. Now if my bond energy of AB is negative, then it will dominate the whole term. So that's why we will finally end up with delta H mix as a negative term. Now what happens if AA bond energy is more negative, AA bond energy and BB bond energy is more negative when compared to AB bond energy? So at first we have AB bond energy as more negative than AA and BB. That means, let me write it so that it will be more clear. So bond energy of AB minus half, because we are only considering one bond, right? So AA so bond energy of AA plus bond energy of BB. This is my total bond energy, right? Now it contains this term. So this omega has this term. It also have other terms like coordination number, like number of Avogadro number, and we do not want those terms here because they are just the multiplication factor. It depends upon the type of atom. So yeah. Now if that omega terms, if we want our omega terms to be a negative term, right? So bond energies are always negative. We know that. So if any time if some bond forms, it releases energy. So bond formation is a energy releasing process, right? It's more like an exothermic process. And even though some reactions are endothermic process, processes. For example, if you want to form a bond, so we need to supply energy. Again, once the bond forms, it will give some amount of energy, right? So yeah, now the total energy releasing from bond the bond formation will be our free energy, right? Now, and some part of will be used in some places and some part will be available to us, and that availability part is known as free energy. So that is we call as a Gibbs free energy. Now, if you want the term to be negative, so if you want to get that immiscibility gap, so that means the delta H mix, and we also know that the delta G mix equals to delta H mix minus T delta S mix. Now we clearly know what is delta S mix based upon configuration entropy. So we are not considering thermal entropy, we are considering only configuration entropy, which is RT XA ln A plus XB ln B. Right, we derived many times, right? So I hope you all know, or if you are not familiar with it, again you can just refer back to previous sessions from 2 to 4, I guess, where I have derived many number of times. So yeah, you people can refer it. So we know the delta S mix is RTXA minus plus RTXA ln A, right? Now minus RTXA ln XA plus XB ln XB. So the minus will become plus. Again, even though it becomes plus, minus or ln XA is already always a negative number, because more fractions are lies between 0 to 1, and logarithmic values between 0 to 1 are always negative. So we need not to worry about this part for now. This will be always negative. Now what about this part, right? So that's how it is. Now, if we are talking about ideal solutions, now what do I mean by ideal solutions? Ideal solutions are nothing but delta H mix is 0. That means we are only dealing with delta G mix will be equals to minus T delta S mix. Now we know the whole minus T delta S mix, the whole term is negative, right? So delta S mix will be RT minus R XA ln XA plus XB ln XB, so minus will become plus. Now because the ln XA terms, ln XA and ln XB terms are negative, the whole term will be negative. So we will form a solid solution like this. So we will form a free energy versus composition like this, right? Let me draw it. So more or less it will look like this. So RTXA ln XA plus XB ln XB is parabola, inverted parabola we can call it as. Now what happens if my delta H mix is negative? The first case, the delta H mix is negative. That means the bond energy of this guy, the AB, this one, is negative. That means we are forming more AB type of bonds. So A type of atoms likes to be surrounded by B type of atoms, and B type of atoms likes to surrounded by A type of atoms. So it's more like a more symmetrical, right? More long range ordering. We will see the ordering. So we'll have more long range type of ordering. So these are the type of compounds which forms stoichiometric type of compounds. For example, Fe3C. Right. So there you can see the long range ordering. Wherever you see, you will find Each carbon atom is surrounded by 4 iron atoms or 3 iron atoms, right? So Fe3C. So 4 atoms and each carbon atom surrounded by this many number of iron atoms. Now that is known as cement type. If it is cement type. Now that is for case delta H mix is negative. Now what about for delta H mix is positive? So for example, let's say we have two cases. So delta H mix is not that dominant when compared to delta S mix minus T delta S mix. That means delta H mix term is positive. So some part is being cancelled out from minus T delta S mix. So for example, if I have minus T delta X mix is like my 25 and my delta H mix is my 5 plus 5, so it will be 20 minus 20, right? So only some part of it is being taken out by delta H mix being a positive term. Now what example? Now for that scenario, so the delta G mix versus composition curve will not change. So it will move upwards. So if I show here, it will more or less like its values will decrease. So it will look like it's moving upward. Right. So it will look like it has moved upwards. Why? Because it has values. On every point of curve, the value has been decreased or increased. Sorry. So that's why the whole total system has increased. Now, what happens if delta H mix is somewhat more dominant? Right. So what happens if delta H mix is dominant? So if my delta H mix is dominant, then it will affect the curvature of this curve, right? So this curvature part is being affected by the delta H mix. So that's what we see. We have a steep curvature. Now we do not have that steep curvature. We have a bit shallow curvature. Now if I try to increase my delta H mix more positive and more have a more positive value, then my delta H mix, then my delta G mix will look like this. So its curvature will change. It will not continue. Right. So you will have a hump in between. So that's why I try to discuss how these humps come now. And because of this hump, you can see, for example, if I am at here. So if, for example, if I am at here, right? So let me draw this diagram here so that it will be more proper. Options. Let me change my ink color. So yeah. Right. So this is my right now. Yeah. It may not be that much accurate, but please. Change my color. So coming back to this now, if I am at here, for example, these are my inflection point where my double derivative becomes 0. Right. So now if I am at here, if my composition is this composition, my x naught composition, just like I have said before. Now if that is my x naught composition, now what is happening? So this is my final free energy after equation, which is a bit higher when compared to this guy, right? So now from here it will try to dissociate, right? So it will try to dissociate. Now we will end up with, just like I have seen before, so we will end up with these two compositions. Now if I draw a common tangent here, if it touches I, so it will look like this. So this is my common tangent. So this common tangent will touch these two extremities, right? If my composition at this point, so it will touch here and here. So that's why if I am below this inflection point, my composition, my final composition will dissociate into two parts, which has x1 and x2. Again, please keep this in mind. Only one type of phase is being dissociated, right? So this type of mechanism, this decomposition mechanism, or we called as binodal decomposition. Why? Because you are forming two different types of compositions, right? So that's why we call it as a binodal decomposition. And again, it needs nucleation. Again, at that composition, when we try to stay at the T2 temperature, because of the undercooling from T1 to T2, there is a undercooling. You will form because of this undercooling, you will have nucleation, and if the T2 temperature is appropriate, you will also have the diffusion. Just like I have said before, if the temperature is too low, for example, if you are trying to undercool it very fast, right? So that means the undercooling is quite high. That means you can easily form a nucleation, right? The nucleation rate will be higher. So we have even derived that part where how the nucleation rate, it depends upon the undercooling, right? So it follows the exponential path. So once we attain a certain undercooling, the nucleation rate will just burst out. So that's what we see in homogeneous and heterogeneous nucleation. For homogeneous, we need heavy undercoolings. For heterogeneous nucleation, we can go with light undercoolings. You will have a high nucleation rate. Now, undercooling means we are reaching very low and low temperature. So again, the next part is a growth part. So growth part depends upon the diffusion of atoms. If you are talking about the diffusion phase transformations, right? Even if in non-diffusionless phase transformations, we need to have a collective moment of atomic planes. So it's more like a pack of cards moving, right? So that's what we see in matencytic phase transformation, right? There is no diffusion of atoms, but there is a collective moment of atomic planes. Now, where there is a formation of twins, because of there is a formation of twins, that's how we accommodate the strain inside during the transformation, right? From BCC to BCT. So from FCC or gamma FCC to BCT, body centered electron construction. Right, so the carbon atoms will try to squeeze, and they get trapped. Try to squeeze away from their position, and they get trapped at the edge centers. So that's why we have one elongated axis in matencyte, and another axis being shrinked, and the third axis will remain same. So that is about diffusionless phase transformation. Now coming to this diffusional phase transformation. Now, we were at the undercooling part, right? So the nucleation rate will be higher for higher undercoolings, and for diffusion, for example, I'm at T2 temperature, and for diffusion to occur, we need a diffusion of atoms. Again, for the diffusion of atoms depends upon the temperature. Higher the temperature, better the diffusion of atoms. Right? So if I try to increase my temperature, the final temperature, then the atoms can easily diffuse from one point to another point, from one location, from one phase to another phase, or they can migrate along the phase boundary. Right, so yeah, so that is how it happens. So the phase dissociation happens in binodal decomposition. Right, so yeah, so in binodal decomposition, so according to that, so what we have said now, so for binodal decomposition to happen, we need a good amount of temperature and also good amount of water cooling. Why? Because it happens conventional. It happens in a conventional process where you need a nucleation and also the grain growth. So for nucleation, you need good amount of water cooling, and for grain growth, you need good amount of temperature. Right, good amount of temperature. So that is the reason why we get at normal homogeneous coolings, you will have perlite, right? But which is not always which is not always the case when we try to cool the steel, carbon steels, right? The low carbon steels. And the reason why because of the undercooling. So if we try to do higher undercooling rates, you will end up with Bennett. And how the Bennett will form because of the low undercoolings, the iron diffusion will become sluggish. And at one point, for lower Bennetts, even carbon diffusion will become sluggish, and they try to come out from the layer structure. Right, so that's why we form upper Bennett and lower Bennett, because of the diffusion of atoms of iron and carbon atoms. Now, moving on to that is about the binodal composition. When my composition is at here. Now, what happens if my composition is at here? It will lie. So here I have said before. So here the dg by dx change is positive. That means the delta d square, the double derivative. So I will just write the double derivative like this. Right. So here my double derivative, and here. Here my double derivative is negative. And here, this point, my double derivative is positive. So, and there are two cases here. Our double derivative, that means the free energy change with respect to composition is positive, and here the free energy change with respect to the composition is negative here. That means the free energy, the slope change is positive here, and the slope change is negative here. Right. Now, that means the free energy change is negative. That means if you are at this composition, we do not even need because of large free energy change, we do not even need to get a nucleation. Right? We do not even need a nucleation growth. Right? It just happens like the movement of atoms, the migration of atoms across the boundary. That's all. Right? You have same type of crystal structure, but it is two different compositions. Right? It is for the same type of crystal structure. So the alpha 1 and alpha 2, here we can see. So once we dissociate, the alpha will decompose into alpha 1 and alpha 2. So alpha 1 and alpha 2 have same crystal structure, but of different compositions. Right? So that means to form a same crystal structure but different composition phases, you need to have only the movement of atoms across the grain boundaries. That's all. There is no movement of atoms from one phase to another phase. It's just the movement of atoms across the grain boundaries, and you have your two different phases. That's all. So that is known as a spinodal decomposition. Spinodal is more like a spontaneous decomposition reaction where you do not even need nucleation part. Right. So that is about the spinodal decomposition. And the binodal and spinodal decomposition, the only difference is about the free energy changes, right? How the slope of free energy versus composition curve changes, and for this it is positive, and for that it is negative, right? So because of that more negative value, so that means the more free, the even at disturbing a small composition, right? So even if I try to disturb my composition from here to here, so that's how it forms, right? So once I quench my sample, and because of a small fluctuation inside the composition, and because of this fluctuation, the change will be so much negative. That means the free energy change is so large, which is again the negative value, decrease in negative value. The whole system has enough amount of energy. It can just bypass the nucleation part, right? It can just form a different phase. How it forms? It forms the migration of atoms across the boundary. So that's how you end up with two different phases. Now, so this is what happens. So at first I was at x2 composition. Sorry, at first I was at x0 composition, right? When I was at T2. When I was at T2, I was maintaining my composition as x0. And even when I quench my sample, right? When I quench my sample, which not to room temperature. Please understand, if I quench my sample to room temperature, I will directly retain my composition or even my microstructure there. Because at room temperature, the diffusion of atoms is more or less the thermal arrest, right? So we are trying to arrest the movement of atoms. We are not giving a chance for our atoms to diffuse or to move, right? So that should be taken in mind, that if I directly try to decrease my temperature to room temperature, that means I'm not allowing my atoms to diffuse. So there will be no partition of phases, right? So that's why what we are trying to do, we are trying to maintain a temperature T2 such that we are giving enough time for the migration of atoms, right? At least for atoms to migrate along the surface, such that they form two different phases, right? Alpha 1 and alpha 2 of different composition, right? And there is another thing: if alpha 1 and alpha 2 are formed in such a way such that if there is no straining, you'll end up with a coherent decomposition, coherent spinodal decomposition. The first one we discussed was the alpha 1 and alpha 2 has two different not crystal structures, but yes, different compositions. So alpha 1 and alpha 2. Now, once my alpha, which is a solid solution, is quenched at T1, quenched to T1, again I have reached the supersaturated criteria. That means I have reached the supersaturation. So my atoms will diffuse, right? So from alpha to become alpha 1 and alpha 2. Now, if they diffuse and they dissociate into alpha 1 and alpha 2, and now the conditions are, so for example, if I say the alpha 1 and alpha 2 has same crystal structure, so that will be more possible way, because the atoms do not have to arrange themselves more, just like in different phases, which requires the nucleation and the other process, right? Now, so you do not need any accommodation like that. So let's say we have only alpha and alpha 2 of same crystal structure, and because of they have different compositions, right? So A is being accommodated more. So for alpha 1 it is rich in A, and alpha 2 it is rich in B. So pure A has a different lattice parameter, pure B has different lattice parameter. And why is that? Because even though they have same crystal structure, for example, if I am saying FCC and FCC, even though they have same crystal structure, they need not to have same lattice parameter, because the A type of atoms has one type of atomic radius, B type of atoms have different type of atomic radius, and that they have different types of electronegativity. I mean different values of electronegativity. So this will result in the different lattice parameter. For example, alpha has A, the pure A has 2.01 angstroms, and B has 2.04 angstroms. So that is a change in lattice parameter. Now, if I try to add B, more amount of B atoms, then the lattice parameter of A will try to increase, right, from 2.01 to 2.012, 2.014. So it will try to increase, and it will reach, when I have total pure B, it will reach to the lattice parameter of B, pure B, right? Now, so the same happens. Alpha 1 is rich in A, it so it means the lattice parameter will be more than pure A and less than pure B. And alpha 2 will have a lattice parameter different than alpha 1. Why? Because it has more number of B atoms in it. So more crystal lattice change can be seen. Right. So once we have a different lattice parameters, so at coherent interface, so again going back to the grain boundary chapter, the interfaces chapter, where we have seen if the two phases have same different crystal structure or the same crystal structure, then they want to accommodate, if the two phases tries to maintain the continuity from grain 1 to grain 2, they need to have a comparable lattice parameter, right? So that's why, so that way they can perfectly match. So here you can see, so let's take the pointer options. So let's say this is my atoms. These are one type of atoms. Let's say these are another type of atoms. Now if so, these are my bond lengths, right, for this guy. Erase that one. So draw different color. Yeah, green. So these are bond lengths for these atoms, right? So now what about blue? So blue also will have a different lattice parameter, the bond length, right? So that is what we call as the lattice parameter. Let's say this is my A type of atoms and these are my B type of atoms. Now if I want to continue this structure, this type of symmetry here, then I can form bonds, right? So you can see there is this bending of bonds, right? More or less you can say there is bending of atomic bonds. That means we are trying to the system tries to accommodate, or the system tries to have a coherent interface where the continuity will have, right, the continuity maintained. You can see there is a one-on-one relation between the atoms. Like this atom is B type of atom is bonded with one A type of atom. So you can see that type of chemistry here. Now that is we call it as a coherency. So there is a perfect one-on-one match between two different types of species. Now what happens if my lattice parameter is a bit different? Now if my lattice parameter is a bit different, as I have shown on the rightmost part, the system tries to accommodate if it can see, if it can assume that there is a minimum amount of energy that needs to maintain, or to maintain the continuity, right? That is one point. That means the system will try to distort the bonds at the interface between the two types of phases, or two grades, to maintain the continuity. Now to distort these bonds we need energy, and that energy is called as a strain energy, right? Now in conventional chemical spinodal decomposition, we do not consider we consider strains, right? So we did not say there was coherency between the phase 1, alpha 1 and alpha 2. We said they're totally incoherent interfaces, for simplicity. So if I'm saying that both the phases alpha and alpha 2 are incoherent, that means there is no strain in between alpha 1 and alpha 2, right? There is no accommodation of bonds, right? They're totally different lattice parameters. So the system said, okay, I cannot accommodate this much amount of strain, so there is no matching between alpha and alpha 2. So that's what we call it as an incoherent interface. An incoherent interface, you have high amount of surface energy being created, right? So why high amount of surface energy? And because there is no matching between alpha and alpha 2, there is no continuity, there is creation of a surface, right? Free surface. Students, a free surface, there is a creation of surface. So in perfect incoherency, there is no matching, so that's why we have a new surface being formed. What about incoherency? In coherency, you have one-to-one match, so there is no need for surface energy being formed. We only have interfacial energy, which is very less when compared to the surface energy being in incoherent interfaces, right? And because there is a bond matching between alpha and alpha 2, there is only the interfacial energy. That's all. The alpha, the grain interfacial energy, grain bond interfacial energy. That's all. There will be no incoherent surface energy, which is quite large when compared to interfacial energy of alpha and alpha 2. Incoherency. Right. Now, if my lattice parameter is a bit different, then that means there needs to be a distortion, and there needs to accommodation of a strain energy, right? And if we do not have any large change in lattice parameter, for example 2.01 to 2.0 01 to 2.011, so very small distortion, then that can be easily accommodated. Then the alpha 1 and alpha 2 will form a coherency, right? So that part we called as a coherence spinodal decomposition, right? So that it's nothing but the alpha and alpha 2 whatever form have a coherent surfaces. That's all. So that is the difference between chemical spinodal decomposition and coherent spherical decomposition, spinodal decomposition. Now, back to this point. At first, I was at T2, and my composition is at X0. So the composition is at X0. So if I try to decrease my temperature, no, if I try to maintain, not decrease, if I try to maintain my sample at the temperature, if I keep my sample in the oil bath for a longer duration of time, so now this diagram, this left diagram shows how increasing temperature, increasing time, sorry, not increasing temperature, how the increasing time will affect the composition distribution. So at first, at time t equals to 0, here at time t equals to 0, right? So at time t equals to 0, there is no fluctuation in composition. Now after time t, at time t equals to t1, here let's say time t equals to t1, there is the dissociation of phases, right? So there is some composition fluctuation, and this composition fluctuation will move, it will grow. I mean, how? So that's what I have said before. So here we can see when I am at this composition, even if there is very slight change in composition, our change, the free energy change will be so large and it will be negative. I mean, the change will be more negative. I mean, our final energy will be more negative when compared to our initial one, and that difference is so large that we can shun our bypass our nucleation part. So that's why it will grow, it will keep on growing. So once the composition increase here, so the composition sideways, at the side the atoms will try to diffuse, right? It's just a grain boundary movement, will start to migrate from this, from here to here, and this keeps on happening until they reach the final composition x2 and x1, right? So this is my phase, let's say this is my alpha 2 and this is my alpha 1, that's all. So that is how the spinodal decomposition happens, right? Now, yeah, coming to what are the different parts that affect our decomposition, our spinodal decomposition, right? We have three parts. But when we are discussing about phase transformation, we discussed three parts, right? One is the free energy, the total volumetric free energy, which is the main reason for any change in phase. One is our volumetric free energy, the next one is our surface energy, and third is our strain energy. Now if I try to write it, so for example, the total change delta G, the total change will be equals to minus V volume of the new phase that has been formed, V delta G V, right? The volumetric free energy minus delta G, the change in free energy with respect to the strain free energy, which is a positive term. Why? Because the minus into minus will be plus. So the sum part of the volumetric free energy is being taken out by the strain energy. Why? Because the system needs some energy to accommodate or to strain those points. So that's why the strain energy is being taken away from the volumetric free energy, some part, like not the whole part. If we say that it is a whole part, then the system will not form, right? Because there is still, we have a, so let me write it in positive term, plus surface area that has been created times the surface energy, right, of say alpha 1 alpha 2, alpha 1 alpha 2, right? The volume of alpha and alpha 2 being formed, and one we have a delta GV, which is the volumetric free energy, and the next one is delta GS, which is our strain energy. Just observing these equations, we have three terms: two positive terms, one negative term. So for delta G to be, if I say for delta G to be positive, that means the two positive terms must dominate, so that the negative term can be taken off. For example, these two terms will combine to give 50 kilojoules, for example, and the negative term will give minus 45 kilojoules. So 50 minus 45, which is plus 5 kilojoules. That means you need to give 5 kilojoules of energy to some system to transform something, like to form a new phase of alpha and alpha, which is not a spontaneous process, right? It is not a favorable process. That means you need to continuously supply 5 kilojoules of energy to start the transformation. So that's what it is, right? And the best way possible is to heat it. You heat something, you give heat energy, and it will transform. That's what happens at high temperature phase transformations. So why high temperature phase transformations do not happen at low temperature? That means the name itself suggests that means we are applying heat energy. It's not like the temperature. Temperature is just a scale, right? We are giving energy. That means at via heat energy we are giving the system to transform. So the heat energy comes from the scale of temperature. So that's why we call it as a high temperature phase transformation, not like high energy phase transformation. Because we can say high energy phase transformation, but it will mislead it more like when compared to high temperature phase transformation. Because that's the only way of supplying energy safely to the system. Right? If I am doing some mechanical work, right, we can even supply energy through mechanical work, but it will deteriorate our sample. Right? Not only deteriorate, it will have different types of effects on our sample. And there are many ways of supplying the energy. So there is a radioactive way of giving supply energy to some materials, but again it will have its own drawbacks, right? So that's why we call it as a high temperature phase transformations, right? Not high energy phase transformation, because high energy phase transformations involve the broad way of telling what type of energy that we are using to make the transformation happens. We can use any type of energy, which is not possible, right? Only we can do is supply heat, that is heat energy, and we do the transformation. So that's what we call as a high temperature phase transformation. That means we are being more specific when compared to which type of energy that we are supplying to the system. Right now, my total free energy is equals to the volumetric free energy, which is negative term and a positive term, plus the area times the surface energy. So that's all. Now, what is the expression for, again, for delta G to be positive, the two terms must dominate, and for delta G to be 0, whatever the volumetric free energy that's being supplied, has been created from transforming one phase to another phase, is being totally sucked by our volumetric strain energy to accommodate the structure, or to accommodate to distort the bonds, and the second one is the surface energy, right? That means the phase is at equilibrium, so it's like standing on a cantilever where you can either transfer, whether you can fall on this side or that side, right? So that's why you are standing at equilibrium. Now when delta G is negative, that means whatever the volumetric free energy that has been obtained by transformation will be more than sufficient to transform, to accommodate our strain and surface energy. So those reactions are favorable reactions, because those reactions will spontaneously transform without needing of any external help, right? Because the system has its own energy, so it can transform. These are the three cases. Now, if we want to know the terms, right? We want to know terms, and this term is my volumetric free energy. Right, and it depends upon again the double derivative of our free energy with respect to the composition and times the composition difference. What is the composition of alpha 1? So this is the composition difference. So alpha 1 composition minus alpha 2 composition, or vice versa. Right, you can take it as alpha 2 x2 minus x1. Right, so the composition difference, alpha 1 minus alpha 2, or x1 minus x2, or x2 minus x1. So yeah. Now if x2 minus x1 is 0, that means there is no suppression of phase, or there is no formation of new phase, right? So that means there needs to be a difference, certain difference of x2 minus x1. Now that is my volumetric free energy, and the next one is my surface energy, or you can call it as delta G surface energy. Right, so it is the surface free energy. Now this is my surface free energy, and this is my volumetric free energy, and the third term is my strain energy. This is my strain energy, and these are my three different types of energy that are uh, being discussed here when transforming one phase to another phase. The first one is my volumetric free energy, which is coming from the transformation of phases from one phase to another phase, and my next one is my uh, one is my volumetric free energy, the next one is my surface energy, and the third one is my strain energy. Now, so from our discussions, our volumetric free energy must be much larger than our strain energy and the surface energy. Right, so these are my volumetric energy, surface energy, and strain energy. Now, so volumetric free energy again depends upon the compositional differences. The strain energy depends upon the difference, and again the strain energy will again depends upon the compositional difference. Why? Because uh, a certain composition will have a certain lattice parameter, right? So my composition defines what is my lattice parameter, right? That's what we have discussed before. So pure A will have a certain lattice parameter, for example 2.01, and pure B will have a lattice parameter of 2.04. So when I'm trying to add B atoms in A, so the lattice parameter will change from 2.01. So the more amount of B atoms go into A, our lattice parameter will change from 2.01. So alpha 1 is more close to pure A, that means it has a bit greater lattice parameter when compared to pure alpha, pure A. And about alpha 2 is very close to B, so it will have a less lattice parameter compared to pure B, but it has a little bit higher lattice parameter when compared to alpha 1. So alpha 1 will have certain lattice parameter, and alpha 2 will have a greater lattice parameter. So the higher the change in lattice parameter, the higher will be my strain energy. So that's what it's shown, and my eta value is nothing but how the lattice parameter will change with respect to the composition. So that's what eta means here. What is the change in lattice parameter with respect to my alpha, or the composition. Now, so my volumetric free energy will depends upon the change in composition between alpha 1 and alpha 2, the difference in composition, and also my lattice the strain energy will also depends upon my change in composition of alpha and alpha 2, and my the surface energy will also depends upon the change in composition between alpha and alpha 2. Right, so that's how the accommodation at the surface changes. Right, change in lattice parameter will also have effect on surface energy. Right, that's what we have seen in when we are deriving for the free energy when Wolf net, right? So when we are trying to derive for Wolf net, we have seen how the free energy changes with the composition. So that's what we have seen in there, how the composition change with respect to temperature. And the next part is about the composition of alpha 1 and alpha 2. Right. So alpha 1 will have a certain composition and alpha 2 will have a certain composition. So the change will give us the strain free energy. Right. Now that is about the free energies. Right. And also my free energy will depend upon the lambda. So higher will be my lambda, that means the size of this. So what do I mean by lambda? So lambda is nothing but my wavelength here. Right. So what is my wavelength? Wavelength is nothing but the distance between two crust or two maximas or between two minimas of any wave. So that is my wavelength. So if I have a certain wave and if I measure the distance between two maxima or two minima will give me my wavelength. Now that means it's more like the thickness of alpha 1 and alpha 2. Right, the thickness of both alpha and alpha 2. That is my wavelength. Right. So if my wavelength is higher, that means my surface area will start to decrease. Right. So it's same for nanomaterials. Just like we have discussed, just like the theory is applicable for nanomaterials. So if I have a bulk volume, it has some surface area, but when I try to break that block into smaller and smaller and smaller pieces, whatever the area that has been inside the volume, that is being taken out. So that's how it is. So if I try to increase my lambda, my surface energy will go on decreasing, because more and more amount of area is being sucked into a volume. Right, whatever the surface area is being coalesced. Two types of grains are coalescing. So if I have two grains, they have different surface area. Now if I try to coalesce to these two grains, some part of surface area will be accommodated inside the volume. So that is why the relation is inverse. So my thickness of alpha and alpha 2 increases, my delta G of surface energy will decrease. Now what does this relation says? Now this relation tells me that this is my total energy. Right, so this tells me this is my total energy. So it's nothing but I added these three terms: delta Gc, delta gamma, and delta G strain. So if I add these three types of energies, what will happen? So if I add these three types of energies, it will form that relation. Right, and for this relation to be negative, that means this term right, if I try to equate it to 0, now if I equate this whole equation to 0, then that means this term multiplied by negative, actually that term is positive, right? So sorry, that term is negative. Now if I multiply that term with negative term, it will become positive. Then that value must be greater than these two values. So what are those two values? This is my volumetric free energy, this is my surface energy, and this is my strain energy. Right. So my volumetric free energy must be greater than my surface energy and also my strain energy. Now then only you will have a spinodal decomposition. So that is the criteria for spinodal decomposition to occur. Right. Now the next part. Moving on to the next part. The next part is the double derivative. What happens if this term, the strain energy term, right? What happens if my surface energy term is 0, right? For lambda equals to infinite, like we have very large wave forming. That means the thickness of alpha 1 and alpha 2 is very large. So that is the case. That means my alpha 1 and alpha 2 are very large. The thickness is quite large. Then my lambda will tends towards infinite. Then what I am remained with is the volumetric free energy and my strain energy. And for the spinodal decomposition to happen, you will need to have the coherent spinodal decomposition to happen. This is my relation, right? So that is about coherent spinodal decomposition, and this is the spinodal decomposition. So this is actual micrograph of analog of spinodal decomposition. Now, how do we get this image? It is taken from BSc image, because in SC image we cannot pinpoint, okay, this is my alpha 1 and alpha 2. Why? Because the alpha, even though for example if alpha and alpha 2 doesn't have very different compositions, right? So the compositional difference is not much. Then alpha and alpha 2, the interface will be acting as a mushy region, right? So to avoid this condition, or to avoid this problem, we do the BSc imaging. In BSc imaging, what happens is we use backscatter electrons. Now backscatter electrons are more sensitive towards the atomic number, right? The higher the atomic number, the higher the backscatter electrons are emitted by that element, right? And because alpha 1 is not richer in A and alpha 2 is richer in B, so alpha 1 and alpha 2 so alpha and alpha 2 have two different compositions, right? So alpha 1, for example, if I take alpha 1 has 40% of copper and 60% of nickel, then alpha 2 has quite opposite percentages. So alpha 2 has 60% and alpha 1 has 40% of copper nickel. I'm just taking for an example. So from BSc imaging you can directly see, so the richer phase will be appearing more bright, because the signal coming from that phase will be higher. Now when we see for alpha 1, which is not the case. Why? Because alpha 1 will be appearing quite grayish in color, dark grayish in color when compared to light gray color. So that is why we see these two different types of grayscale images. One we have a light gray, I mean more brighter image, and the black is more darker image. Right. So that means the lighter image is alpha 2, and the darker more gray area, gray region will be our alpha 1. So that is how we see the alpha 1 alpha 2 decomposition SE images. And when we do the elemental composition for a line scan, for example, if I draw a line and I do the line scan, my composition will so my composition will change. Right, so the compositional change will look like this, the way. So that's why we are trying to represent this compositional changes in waveform. So our composition, we have the compositional difference in alpha 1, and alpha 1 will be more have less composition of B when compared to alpha 2. Now that is all about phase transformations, and this is the last phase transformation, which is spinodal decomposition. And again, the spinodal decomposition, I will just briefly recap about spinodal decomposition. Spinodal, these type of decomposition, the decompositions appear because of the immiscibility gaps, right? So because of this immiscibility gaps, again there are two types of decompositions. One is binodal decomposition and another is spinodal decomposition. So binodal decomposition has the double derivative with respect to the double derivative of free energy with respect to composition is positive, but for spinodal decomposition the same is negative. Right, the double derivative is positive there, and the double derivative is negative in spinodal decomposition. Now, what are these effects? So, for double derivative, positive means the free energy change, the slope of free energy curve is positive. That means if we change the composition of a free energy, if we change the composition, then the free energy change will be positive, right? So that means there is a need for a nucleation to happen. Now, what about the free energy change? The double derivative of the free energy with respect to composition negative. That means the free energy change with respect to x, or the slope of the free energy change, is negative. That means the free energy with respect to the composition will be so large, and also the negative value, the final free energy becomes so negative that we can directly shun the nucleation part. That's why the binodal decomposition and spinodal decomposition are different from the mathematical terms we can define. The binodal decomposition requires nucleation, whereas the spinodal decomposition do not require nucleation. Right? Now, that is about spinodal decomposition, subarachnoid decomposition, and the next part is the recovery recrystallization grain growth. Now, after the phase transformation, to improve the mechanical properties, we do the cold working. Cold working is nothing but the deformation of a material. Now, deformation can be done by different types of process, and one most industrially applied process is cold rolling. So in rolling, we decrease the dimensionality of areal dimensionality of a sample. So for example, if I have a 5 diameter or 5 cross 5 mm cross section of steel bar. So if I try to put it between the rollers, and if I try to decrease the aerial dimension, that means if I decrease the thickness to 2 by 2, right, that means the length will increase. So that is what happens in rolling, right? We try to decrease the aerial dimension, that means the other length dimension will increase, because the material has to conserve, right? The volume has to conserve finally. So that is what happens. Now during cold work, what happens? So any type of deformation process introduce dislocations. Uh, for certain amount of materials, we can even see twins, and certain materials introduce dislocations, twins, and even vacancies. Now, and these dislocations will increase the strength. So it is there in mechanical metallurgy. The introduction to mechanical metallurgy, you can just indicate and how this strength increases. And when I'm discussing about strength, there are two parts, there are 2 points that should come in mind. One is the yield strength, and the second one is the ultimate tensile strength. So when I'm talking about strength, these 2 parts, I'm more directing towards these 2 points. One is the yield strength and the ultimate tensile strength. So yield strength is nothing but the point, the minimum amount of stress that needs to be applied for a material to start the plastic deformation. In more layman terms, that is our yield strength. And the ultimate tensile strength is nothing but the maximum amount of stress that can be applied to a material without making it fracture, right? Without destroying a material. Or the maximum amount of deformation, there can be maximum amount of stress that can be applied such that the material doesn't fracture. Right, in layman terms, these are the 2 terms that I'm implying. Right, yield strength and ultimate tensile strength. Now, if my strength increases, the hardness of the material will increase. If my strength increases, then again my ductility will decrease. Right, that is obvious, because the ductility is nothing but the maximum amount of length that you can deform a material. Right. Now, how this strength, the yield strength of a material, how the strength of the material increases, it depends upon the deformation. So the more amount of deformation, now for deformation to happen, there is a need for a moment of a dislocation. Right. So if a dislocation moves, then only the material will deform. That's what we have seen in previous lectures. So a material to deform, there is a need for a deformation. So that is what it means for a material to undergo deformation. Right. Now, after deformation, so if I say I did my cold working or I did my rolling for 40%, that means my area reduction is 40%. That means my difference in area divided by final area. So that means final area minus initial area upon initial area. It tells me about the total rolling, right, or total cold work percentage, rolling deformation, how much cold work has been performed. So if I say the 40% in reduction now, and because of the deformed state, at first we have high density of dislocations, so there are more number of dislocations, right? So there are high internal stresses that's being in the material, and there is a high defect density. That means there is a high number of dislocations, these vacancies, So now what happens if I try to increase my temperature? Now once I do my deformation, now if I try to increase the temperature of the sample, so that is what I am doing here. So if I increase the temperature, then because of that, so increase in temperature means I am trying to giving energy to the atoms inside the sample. So these atoms will try to move now, and because of this movement, so in recovery process, so what happens is in recovery process, whatever the dislocations, the high density of dislocations were there, so they will try to arrange themselves. So before, the dislocations were tangled, so there were randomly, there were everywhere there were dislocations there. But now because of the increase in temperature, so before it, there were dislocations everywhere, right? They are more tangled in a way. There is no specific arrangement, right? So there were positive dislocations, there were negative dislocations, which were randomly arranged. Right. Now if I try to increase my temperature, like now again there is a temperature scale. So I am talking, for example, if I am talking about a material, so this is my Tm, which is my melting point, and this is my room temperature. Now my whole scale doesn't lie beyond my melting temperature. Okay, so it lies between Tm, 0.1 of Tm, 0.1 fraction of Tm. Here somewhere it lies 0.5 times of Tm, and above that you have 0.6 times of Tm, 0.7 times Tm, 0.8, 0.9 and Tm finally. So it is a reference scale of melting temperature of any material, of a given specific deformed material, right? Now if my regime is between 0.3 to 0.2, it is called as a warm deformation, and if it is above 0.5, then we call it as a hot deformation. If it is below 0.3 to 0.1, then we call it as a low temperature or cold deformation. So above 0.5 Tm it is a hot deformation, below 0.3 Tm it is cold deformation, and between 0.5 and 0.3 it is called as a warm deformation. Now if I am doing between at 0.45 times Tm, so it is more a warm deformation. So what's happening is, because I am supplying certain amount of energy as a heat energy, that means I am giving atoms to move. So dislocations are nothing but extra half planes, so they are also atoms, right? So now because of increase in energy of the system, these dislocations will arrange themselves in certain manner as an array of dislocations, right? See, you can see here. Before, there is a random distribution of more entangled dislocations. Now because now there is no entanglement of dislocations. Here we can see the perfect arrangement of dislocations, and you can say if we have edge dislocations, they arrange in a array manner, and they more or less likely they form low angle grain boundaries, right? So you know the low angle grain boundaries are accommodated by the array of dislocations at the interface, right? Now, and because of this, just besides these dislocations, we have a strain free area, right? So that's why we had this strain free grains that are being formed. Now once we form a grain boundary, which is the grain boundary, because of the parallel array of dislocations, this will move to take out more number of to take out more number of dislocations, right? It moves towards the region where there is more number of dislocations. the high density dislocation area, right? So that's how these strain free grains starts to form. So you can see we have at so at recovery we have partial defect annihilation. So what is my partial defect annihilation? That means um, so somewhere, for example, if I have a positive and negative dislocation, positive dislocation is nothing but extra half plane. So positive dislocation is nothing but at one point I have at from if I see from one specified position. So if I am seeing from here inside a material, I have an extra half plane here and I have an extra half plane here, right? So that means it is called as a positive dislocation, this is called as a negative dislocation. It's just the point of view, that's all, from point where we are looking at. So at one point they will coalesce. That means these two planes will get attached, right? That is nothing but a total plane. That means the two dislocations are being annihilated, right? The two dislocations are being disappeared because the positive half plane from above and the positive half plane from below, when they come in when they come near to each other, that means we have total one plane, right? So that means the annihilation of dislocation. So that is about the partial recovery, and this partial recovery of annihilation of dislocation is quite low, because to find two opposite sense of dislocations is I shouldn't say rare, but it happens, but it does not happen, or it more frequently inside the material, right? So it is low when compared to normal recovery. So after that you have the rearrangement. So this is the main cause for the recovery of strength, right? So the rearrangement, just like I have shown here, the dislocation rearrangement here. So this is the dislocation rearrangement, and this dislocation rearrangement results in the formation of new strain free areas, and because of this the new strain free grains will be formed. And where they will form? They will form at grain boundaries, again because the grain boundaries will provide as with the accommodation for dislocations. So that is the perfect place to accommodate those dislocations there at grain boundaries. So once the dislocations gets accommodated at certain points, that part will become a boundary, and part besides that will become strain free region, and that's why we call a new area being born there. So that is the new grain, or we call it as a strain free grain. And if we give enough amount of time, so this rearrangement will happen for until the whole system will have minimum amount of energy. That means whatever the stresses there will go on dissociating, and the more dislocations will be annihilated, the vacancies will be dumped into the grain boundary regions, or with the help of vacancies the dislocation will climb, right? So the vacancies will get annihilated there. So all these different types of process will happen inside the material when we give enough temperature or enough amount of energy being supplied to the sample. So now once we found, we will have a different different morphology, right? That means these new strain free grains will form just like a heterogeneous nucleation, and we have a fine grain structure. Now again, if we give enough amount of time, this fine grain structure will grow, and they will small grains will be taken out by big grains, and it depends upon the morphology of the grains. So yeah, so this is our final structure. Now this is about recovery, recrystallization and grain growth, and I'm not going to go deep into it because it itself has a lot of, it itself requires 2 to 3 sessions, so I just barely brush up now. And the final part is again the cold work. So it's just a brief summary. So by doing cold work, there is increase in point defect density and also the dislocation density, so which results in increasing strength of the material, because the more and more number of dislocations are being created inside the grain. So now again, for deformation to happen, these dislocations needs to move. Now dislocation, now grain boundaries act as obstacles for dislocation, right? So more and more amount of dislocations will be piled up at grain boundaries, and these dislocations, whatever uh, that are piling up at grain boundaries, will uh, have a back stress on the dislocations that are being moved towards the grain boundary, which will create its own strain fields, and these strain fields will make sure that they get uh, not get near to each other. Just like magnets of north and north pole, you need to give an amount of energy so such that they get close to each other. So the same happens for the dislocations also. So because of that, the strength, the yield strength will be increased, or the stress that needs to deform a material will be increased when the dislocations are being more and more are being created inside the material. Now, so material tends to lose the stored. Once we do the annealing, that means we increase the temperature, we give energy for the atoms to move. That means they will, the dislocation, whatever the defects that are being created, they will be arranged in a certain way such that the material will try to lose whatever the strain energy that has been created inside the material. So the material will try to lose this stored energy, and again it will become softened. Now, once I do the cold work, and we have two things. If I do the annealing at low temperature, I will only have a recovery, so there will be no strain free grains will be formed. Only there will be recovery, and when I do the high temperature annealing, I will have recrystallization. So I will have new strain free grains, and if I do even more amount of time, they will even increase the size of the grains, and the grains will be coarsened. So that is about the recrystallization. So that is about the recrystallization, recovery, recrystallization, grain growth. And most of the cases people try to avoid the grain growth. Why? Because once we have a new fine grain structure, so fine grain structure is more applicable when compared to coarse grain structure, because fine grain structure has a better mechanical properties. So why? Again, in fine grain structure, because of the small grain structure, the dislocations that are being created will have to jump from one grain to another grain. So dislocations can only move in a specified direction. So that's we call it a slip system. So for FCC, it is on 111 plane and 110 direction. Right. So these are the slip system. So dislocations have to have that slip system for them to move, and they cannot abruptly change the direction. So at grain boundary there is a change in planar directions, right? So for example, just like I have shown in initial, where what is the difference between grain 1 and grain 2 of same type of phases. So the orientation of atomic planes. So dislocation have to change the direction according to that atomic plane, right? So which is not which happens when we given enough amount of energy, when we deform material to a certain level. But the dislocation will not move until we apply that amount of yield stress, right? That amount of energy is not given, that amount of deformation is not given. So it will oppose whatever the dislocations that are coming from the grain, inside the grain, to the grain boundary, right? Because the dislocation starts piling up at the grain boundary. So so the dislocation starts piling up at the grain boundary, and they cannot move, right? Dislocations have their own strain fields, so they will try to repel the dislocations, one dislocation to another dislocation. So they will try to maintain a gap because they cannot coalesce, right? Because they have strain fields around them, just like magnets. The north pole cannot coalesce because of the magnetic field around it. So the dislocations cannot coalesce. So they will try to repel each other because of the strain fields. Now that's what we call as a backstress. So backstress is nothing but if we try to push second dislocation towards the first dislocation, which is at grain boundary, the first dislocation which is at the grain boundary will push the second dislocation which we are pushing towards the grain boundary. So that is we call it as a backstress. So to remove that, we need to do deformation, more amount of deformation. Now, if I have a small amount of grain size, that means more is the grain boundary, higher will be the dislocation pile up, and higher will be the back stress being applied. So that's why people stop at finding the structure. They do not give enough amount of time to have a coordinate structure. That is the famous relation, Hall pitch correlation, where the yield strength will increase with decreasing the resistance. So that is about the recovery reconstruction grain growth. Now next week will be our final session on phase transformation materials. We will have extra session where I will just go through every session topics that I have covered, or anything that I have missed, or the proofs that I have missed. That will be covered in extra session, which is of 2 hours. So which will be on April 16th, I guess. So I haven't decided the date yet, but yeah, you will get mail who have enrolled for this course. So thank you. That's all. If you do not have any sessions, you can leave the session.